This is lesson 3.1 for 8th grade accelerated math, an introduction to exponential equations. Okay, to start off, you have this paper that talks about what exponential equations are. So as you know, with linear equations, they have a certain format, and the one that we're used to seeing the most is y equals mx plus b. And that's good to have that because we know that the slope is m and the y-intercept is b, and if I knew the slope and the y-intercept, I'm easily able to graph a line. And so every single type of equation has a certain form that tells us interesting things about it. So with exponential equations, there are certain things that we know about an exponential equation. So what we call the general form of an exponential equation is y equals a times b to the x. So b is raised to some power x. It's multiplied by a number right there. Now there's some restrictions that have to happen in order for it to be an exponential equation. So first off, the letter A stands for the initial value, aka y-intercept. So whatever the y-intercept is, that's going to be right there. B is the growth or decay factor. So growth is when something gets bigger, decay is when something gets smaller, and a factor is what you multiply it by. So if I multiply by 3, that means that it's going to be, so this number right here is going to be multiplied by a factor of 3, and it's going to be done this many times. Now, in order for this to be an exponential equation, b has to be greater than 0. That means that you can't have any negative numbers right there. So you can't say like 3 times negative 2 to the x power. That's not an exponential equation. So you have to have something greater than 0. Now, it can be decimals, so it could be like 3 times 0.5 to the x power. That is an exponential equation. Okay, the next thing is x, the exponent right here. That's the time or the number of cycles, the number of times that something happens. And the final output will be our y. We're used to seeing that. Now here's a couple of clues for you. If b is greater than 1, then it's exponential growth, so it's getting larger. If b is between 0 and 1, it's exponential decay. So for example, for growth, if you had like 1, 2.7, 1.03, those are all growth. If you had something like 0.5, 0.9, 0.01, those are all decays. And if you think about it, if you take a number, like let's just say 100 to make it easy, if I multiply it by something bigger than 1, so 1.1, if I multiply it by that, it's going to be bigger than the initial value. However, if I take that and I multiply it by something less than 1, it's going to be less than the initial value. So this is growth, and that's decay. All right, now when we have specifically growth, okay, when the initial value is increased by a percentage, so we're going to say that something is growing by 3% or something like that, we have this way to write it. So we're going to have a is still our initial value, so it's, if you say y equals a times b to the x, this is still our a. 1 plus r is equal to b. That's actually what that says right down there. So 1 plus r is going to be my growth factor. Now, the thing about growth, it's getting bigger, and that's why the plus sign. R, rate of growth, you're always going to turn your percents into decimals. So percents go to decimals because you can't do math with percents. We always change them to decimals. And again, x is how many times something happens. Exponential decay, you're going to be taking it down, and that's why it's a minus sign. Everything else is still the same. 1 minus r is a decay factor. Now, when we're dealing with exponential equations, a lot of times we'll have some special words that give us clues. So if something is doubling, that means it's growing at a factor of 2. If it's tripling, it's growing at a factor of 3. Quadrupling, growing, factor of 4. If we say half-life or half, it's decaying or getting smaller, but the factor would be 1/2. Notice it's not negative 1/2, it's 1/2. So if you say 10 and it's decaying by a factor of 1/2, then if I take that one cycle, that's going to give me 5. So it's getting smaller. Okay, now let's go into some actual equations. So first off, look at the two tables in 1 and 2, and I want you to find the pattern and then graph what you see. So table 1 will be graphed right here, table 2 will be graphed right there, and look for ways that they're the same and that they're different. So pause this video, do all of those questions, and then come back. Okay, hopefully you found the pattern in number 1. number one, you notice that as the days go on, what's happening to the bacteria? It's adding 2, but that doesn't hold true, so you've got to think of something else. So what is happening that we could also say, if you say you're multiplying by 2, that's correct. It's happening every time you're multiplying by 2. So I'm going to say that you're multiplying by 2. That's the pattern. If you look at number 2, every time the days go on, you're adding 2. So plus 2, plus 2, plus 2. So we're going to add 2. Now if I go to graph the first one, if I go over 1 and up 2, watch your scale. So day 1, 2 bacteria. We better put our labels here. Remember, if you're doing graphs, if you have a story problem at all, you have to label. If I have 2 days, I'm going to have 4 bacteria. If I have 3 days, I'm going to have 8 bacteria. And if I have 4 days, I'm going to have 16 bacteria. Now look at the next one. If I have, again, days and bacteria. So day 1, I'm going to have 2 bacteria. So far that's the same. So the same. And day 2, I'm going to have 4 bacteria. So it's the same for day 1 and 2. Okay, that's one way that they're the same. And then 3 is going to be 6, and 4 is going to be 8. Okay, so that's where they're different. Okay, so days 3 and 4 are ways that they're different. So what are some other things that are the same? What do you notice about this graph compared to this graph? What do they both do? They're both increasing. Okay, what they're doing differently is how fast they're increasing. Okay, so which one do you think is getting bigger faster? Obviously 3 is getting bigger faster, so number 3 is growing faster. They're both growing, but one is doing it a lot faster. Okay, so in the next set of questions, for each exponential function, we're going to identify the initial value, the rate, whether it's growth or decay, the time, and y, round to the nearest hundredths. So you'll find that in these questions, we are going to be doing some rounding of our decimals. Okay, so number 1, remember on your first page, you can go back and look at that, but remember that it's a times b to the x power, and remember what a stands for, b, x, y. So my initial value is 40. Okay, that's what we start with, 40. Okay, now looking at b, which in this case is 3, is that going to be growth or decay? So it's bigger than 1, so it's going to be growth, and it's going to be a factor of 3. And how many times is it happening in this problem? So how many times it's happening is 7 times. So 7 equals time. So that's what you're going to do on all of these. So as you look at number 2, you notice that this one is that equation y equals a times 1 minus r to the x power. So that tells me that my initial value is 1529. And I know that since it's going down minus, it's decay. Okay, now my factor is, what is 1 minus 0.09? It's not just 0.09. Okay, my factor is going to be whatever 1 minus 0.09 is. So 0.91 is going to be my decay factor. That means that I'm going to have 91%. I just won't have 100%. I'll be losing 9%. This is something different, the rate of decay. So how fast is the decay happening? That's going to be 9%. So those two things are different right there. The rate of decay and the decay factor, those are two different things. Okay, and then how much time is happening? 3. So 3 equals time. Okay, pause for number 3 and 4. You do them and then come back and see if you got it right. Okay, number 3, the initial value is 6. It's a growth factor of 1.75, and the time is 10. In number 4, the initial value is 120. 1/3 is less than 1, so it's a decay factor of 1/3. And then time is equal to 7. Okay, the next section, we're going to determine if this scenario would be modeled by a linear equation or an exponential equation. So remember that a linear equation Oh, that was one thing I was going to say up here. This is linear, and this is exponential. Okay, so all exponential equations, they are going to grow like that. Linear equations are a constant rate of change. Exponential equations are not a constant rate of change. When we look at a situation that has linear versus exponential, if there's a percent involved, it's not going to be linear. Okay, linear is a constant amount, so add 3, add 3, add 3. But on the other hand, with exponential, if you add 3%, the 3% is a percent of something, and every time that'll be different. So let's just take an easy question. Like, let's say we start with $100. And if it's going to grow by 3% every year, the first year I'm going to get 3% of $100, which is $3. So the next year I'm going to have $103, and then I grow 3% of that. So when I do 3% of 103, I'm going to get 3.09. So the next year I'll have 106.09. So it's not growing by $3 every year. It's growing by 3%. If it was just growing by $3 and it was linear, it would be 103, 106, 109, and you're not really going to have any, decimal issues there. That's how I know. So as I look at A, B, C, and D, Jan increases her walking distance by 0.15 miles every day. So every day we add 0.15 miles, add 0.15 miles. That's a constant rate of change, so that is linear. Okay, the next one, Jan increases her walking distance by 15% per day. So let's say that she goes 1 mile, and so then the next day she's going to increase it by 15%. So 15% of a mile would be 0.15 times 1. So she's going to increase it by 15%, so she'll go 1.15. Now the next day, she's going to add 15% of her 1.15 miles. So she's going to add 0.1725 to her 1.15. You can do these calculations on the calculator along with me, but the next day, instead of 1.15, she's not going to go 1.3, she's going to go 1.3225. So what I did was I said 1 mile was the first day, and then I added 15%, and 15% is 15% of 1 mile, and that's where I got the 0.15. Oops, 1.15. The next day, we're going to add 15% of the 1.15. And so that's where I got the 0.1725, and so when I added 0.1725 to that, it gets 1.3225. So remember that percents are a percent of something. Percents never work by themselves. You always have to have a percent of something. And so that's one of the reasons why whenever you're dealing with exponentials, you're dealing with a percent. It's a percent of something. So this is exponential. Okay, the next one, the amount of water in a pond decreases by 10 gallons every week. So if you start with 100 gallons and you decrease by 10 gallons, decrease by 10 gallons, decrease by 10 gallons, that's going to be linear. On the other hand, if you decrease by 10% a week, so 10% of 100 is 10, so the first week I would lose 10 gallons. But the next week I'm going to lose 10% of 90, which is only 9 gallons. And then I'll lose 10% of 81, which is 8.1 gallons. And I'm not sure what that is off the top of my head, but anyway, you get the idea. That's going to be exponential. Okay, the next question, it says the population of a small town is increasing, that's a clue, at a rate of 4%. So if the rate is 4%, we have to change that to a decimal, so 0.04. There are currently 6,000. That's my initial value. Write an equation and fill in the table, round appropriately. Round appropriately means you can't have parts of a person. So the equation is going to be y equals my initial value, and then 1 plus the rate. So we're growing by 4%. We get to keep 100%. So this 1 is for the 100%. We get to keep all 6,000 people, plus we're going to add 4% of it, and we're going to do that for X amount of years. So you're going to get your calculator now, and you're going to take this one at a time, and you're going to plug in these numbers. So you're going to say, first of all, for 0 years. So this is at the beginning. So I want you to try this on your calculator, but you're going to, 1 plus 0.04 is 1.04. You can just say that to the 0 power. Put that in your calculator, put your number right there. Next, you're going to do 6,000 times 1.04 to the first power. 6,000 times 1.04 to the second power, and then the fifth power and the eighth power. And then round it to the nearest person, come back and make sure that you did your chart correctly. Okay, here's numbers you should have gotten. I did round to the nearest person, and I had to do that on these. Now, the great thing about knowing these exponential equations is, you know how before when I did like the gallons of water and I said, 10 or 100 gallons down to 90, down to 81, and then you have to keep subtracting a weird amount, and like with Jan walking and stuff, you don't have to do that here. This exponent part, it takes care of that addition over and over. Add 15%, add 15%, or add 4%, add 4% to your new total. And so every time you do it, it's like this whole complicated thing. So the equation right here takes care of all of that for us. So make sure you got these numbers correct, and then we're going to continue this lesson on the next video.